This next equilibrium problem, we have an object on an incline, so it's a little bit different than all these other problems where it's been on a level surface. And so we want to learn how to proceed if we are on an incline. There's a little trick that we'll learn. We have a 5.4 kilogram bag of groceries, an equilibrium on the incline with an angle of 15 degrees. We want to find what is the normal force of the incline on the bag of groceries. So we'll start by drawing our free body diagram. So the force is present. We have gravitational force. I assume we're on the Earth. So gravitational force always acts down. Then we're on a surface. So we have the normal force. The normal force is perpendicular to the surface. So I'll try and trace that right here. Label it as the normal force. And we have friction preventing it from sliding down the incline. So the friction is going to be parallel to that incline. It does not tell us whether or not it is moving. It could be either at rest or moving at a constant velocity. Being a bag of groceries, however, I'm going to assume that it's not moving, so I'll label this as static friction. But it doesn't really specify. The next step is to write down our givens. And so we know that the mass of the groceries is 5.4 kilograms, and the angle is 15 degrees. We want to find what is the normal force. First step, if you're given the mass instead of the gravitational force, solve for the gravitational force by multiplying that mass by the gravitational field constant. So we take 5.4 kilograms and we multiply by 9.1 newtons per kilogram. We get that gravitational force to be 53.0 newtons. Now we have two forces that are in neither the x nor the y direction. So let me bring this Cartesian coordinate system down to see that. So I see that the normal force and the static friction would have to be broken into their x and y directions. But instead of doing that, here's our trick. If we rotate that coordinate system so that the x direction is parallel to the incline and the y direction is perpendicular to the incline, we only have the gravitational force, only one force to break in x and y components. So it saved us a lot of time. And that is exactly what we're going to do. If we rotate that coordinate system, now we just have to break the gravitational force into, I'm going to label this as the perpendicular component, because it's perpendicular to the incline, and the parallel components, because that's parallel to the incline. But in order to do so, we need to know an angle. And it turns out that this angle at the top of that triangle is the same as the angle of inclination, that is 15 degrees. And so now we are going to take this gravitational force, since we rotated our axes, we take this gravitational force and break it into its perpendicular and parallel components. I'm going to draw this to the side. So I'll label it as 53 newtons, or in this case it's my hypotenuse. And then my perpendicular and parallel components. Label my angle as 15 degrees. So to find the perpendicular component, let's do that first. To find the perpendicular component, that is the adjacent side, and so we want to use cosine, 53 newtons times the cosine of 15 degrees. And we get the perpendicular component to be 51.2 newtons. To get the parallel component, that is the opposite side, and so we want to use the sine to get the parallel component. And we get the parallel component, comes out to be 13.7 newtons. So let's pause here, see what we've done so far. Draw our free body diagram, write down givens and what we need to find. If we have the mass, solve for gravitational force first. Any forces at angles, break into x and y, or perpendicular and parallel components. And now we proceed to our conditions of equilibrium. So our conditions of equilibrium are that the total force in the x direction is 0, and also the total force in the y direction are 0. They all balance out. All these forces balance out. So in the x direction, we have the parallel component, which is to the left, so that's negative. And we have the static friction, which is to the right, so that's positive. Again, our new sense of positive and negative according to our rotated Cartesian coordinates. We know the parallel component, so negative 13.7 newtons plus the static friction is 0. Solve for the static friction. It turns out that it's the same 13.7 as the parallel component. In the y direction, we have two forces, the normal force and the perpendicular component. Remember, we are not using this gravitational force anymore. We replaced it with its two parts. So we never use that again. Once we get its two components, we never use that again. Writing perpendicular and parallel components is the same as just writing the 53. It's an either or. Either you write the 53 or you write its two parts. You don't do both. So we're replacing it with its two parts. So in the y direction, we have the normal force, which is up, and we have the perpendicular component, which is down. We know that perpendicular component, which is 51.2 newtons. So we solve for the normal force to also be 51.2 newtons. If we look back at what we were asked to find the normal force, so here is our answer.